Hello everyone, I'm Fangchen from the Chinese University of Hong Kong, Shenzhen. It's my great honor to share our recent work, DocReal, robust document developing of real-life images via attention-enhanced control point prediction, which was accomplished during my internship at the Vivo AI Lab. The contents are divided into the following four parts: introduction, method, evaluation, and conclusion. First, let me introduce the background. In our daily lives, we often use smartphones to digitize documents instead of conventional scanners. Captured images may have diverse physical deformations, resulting in distorted document images. Our task is documenting image dewarping, which means we want to recover the flattened image from the distorted one. The control point method DDCP, a popular solution to image dewarping, is to sample control points on the distorted image, then remap these points to reference points, and finally use interpolation to obtain a complete image. The control point model, while straightforward in deployment, faces three major limitations. Firstly, there is residual background in the rectified images. Secondly, it may output curved text and reduce readability, as shown in the following examples. Lastly, there is a notable disparity between training and real-world data, like the unreal deformation in this figure, which may limit the model's performance. To address these issues, we propose a robust control point-based model. Specifically, our pipeline comprises two subnetworks, Enet and AECP. Enet is a fully convolutional encoder-decoder proposed by the SIGGRAPH paper to produce a coarse result with a global shape through edge-based dewarping. On the other hand, AECP is an individual network that enhances this coarse result by predicting accurate control points for local deformations using attention-enhanced modules. Combining these two subnetworks, our pipeline significantly removes background noise and enhances the readability of developed images, providing a robust and reliable solution. To enhance the quality of training data, we develop a new method that synthesizes 2D training data with 3D deformation to make it more real. There are four steps. First, we extract a 3D mesh from a 3D image in the Doc3D dataset by generating a point cloud from 3D coordinates and transforming it into a 3D mesh. Second, we randomly set camera distance and shooting angles in the 3D coordinate system to map control points in the 3D mesh to 2D control points. Third, we generate a 2D distorted image with 3D deformation by mapping the reference points of a scanned image onto 2D control points, then interpolate the pixels. Finally, we randomly add various noises to scanned images, such as more patterns and shadows, to enrich the synthetic images with random background. While the Doc3D dataset offers a range of 3D deformations, it lacks true curling of book types. To address this, we simulate the curling of books using formula and add additional folded deformations for training data augmentation, thus achieving a more robust model performance. Specifically, we simulate four different deformations, including unidirectional curling, S-shaped curling, kernel folded, and edge folded. Next, we need to perform evaluations on the benchmark. Although DocUNet is the most commonly used benchmark dataset, it only contains 130 images with almost exclusively English text and limited document types. To better evaluate the performance in real life, we propose the first Chinese distorted image benchmark for the DocReal, which covers a wide range of real-life document image scenarios. DocReal includes 200 images with 5 different deformations and contains 3 scenarios, including work, study, and daily life. We believe that DocReal will be a valuable benchmark for the development and evaluation of document image rectification. You can scan the QR code for more information. In quantity comparison, we compare the performance on 2 benchmark datasets, DocUNet and DocReal. The results in Table 1 show that our method achieves state-of-the-art performance in terms of image similarity and OCR performance. Specifically, higher MS-sim and lower LD mean better image similarity between the developed image and the ground truth. Lower ED, and lower CR mean better OCR performance with better readability. In qualitative comparison, we first compare the performance of background removal. From these figures, we can see that our method effectively removes background, while previous SOTA methods exhibit comparable numerical results. They still face challenges with residual background, which may be caused by environmental noise such as obstructions, similar background colors, and other noises. Next, we compare the performance of text readability. As shown in these figures, we show Enet's potentials to cause secondary deformation and reduce the readability. Naively combining Enet with DDCP may result in worse readability due to inaccurate control point prediction. Thus, we combine Enet and the attention-enhanced control point module to arrive at a robust solution with a well-captured document body and improved readability. In conclusion, we first propose a robust model for documenting image developing tasks, which adopts Enet to effectively remove background noise, adds an AECP module to capture local deformation, and finally achieves SOTA performance on 2 benchmarks. We also augment training data by synthesizing 2D images with 3D deformation and simulating additional curling and folded deformations. Last but not least, we provide a more comprehensive benchmark, especially for the Chinese real-life scenarios, including 200 distorted images. That's all. Thanks for your attention.